So the next one is we want to talk about the sufficient condition for tightness. So if we can find a function, let's say phi x, which is a positive function, such that this phi x goes to infinity as absolute value of x goes to infinity, and the sup of the integral of phi x on the dfn is finite, then fn is tight. So that's the sufficient condition that that makes fn tight. So to prove that, let's try to use this condition to prove that this will be less than or equal to some epsilon. So 1 minus fn with some constant m plus fn minus fm is just the two tails, right? The two tails of integral, which is just this form. And but so this is just integral of a function f, function 1 here. But if we divide phi x by so absolute value we are integrating on x greater than or equal to m. So if we divide phi x, which is a positive function, right? We found a positive function here, and divided by the infimum of phi x on absolute value of x greater than or equal to m. So what it tells us that this division is always greater than or equal to 1. So this integral will always greater than or equal to this one, because this integral is integrating a function 1, and this is integrating a function that is greater than or equal to 1. So this is how we get this inequality. And this is less than or equal to, but this is a constant, we take out the constant, and this is integral on this set x absolute value of x greater than or equal to m. We can remove that because we get an inequality of this one. And so if we take the lim sup of this inequality here, then we get the supremum of that, which is c divided by a constant. And this constant is infimum of x greater than or equal to m on phi x, because phi x goes to infinity as absolute of x goes to infinity. Then we can always make this number as small as we want by making the infimum of here to be as large as we want, right? So this can be made as small as we want, less than any epsilon we want. So this proves that this is less than any epsilon, and that proves fn is tight.